In this video, we are going to look at how to eliminate the parameter. We know that the parameter is the variable t. And so we know that x is a function of t and that y is a function of t. Sometimes it's useful to eliminate the parameter. In other words, to write x and y as a function of each other and not as a function of t. By doing this, we can get a better feeling for what the graph of this function is, because we're used to looking at functions y as a function of x, or even x as a function of y. So to do that, take each of the two functions and just write them without functional notation. In other words, instead of saying x of t is equal to t squared minus 3, just write x is equal to t squared minus 3, and write y is equal to 2t plus 1. Then all we have to do is select either one of these equations and solve it for t. Look for the easiest equation to solve for t. So what was done here was taking the second equation, where y is a function of t, and solving it for t. Then it is just a matter of taking that value of t and subbing it in for t in the other equation. In this case, it would be x equals t squared minus 3. We're taking out the t and we are putting in y minus 1 over 2 minus 3. And then just simplify that. And so this simplifies to y squared minus 2y minus 11 over 4. And that is the process of eliminating the parameter. So let's try a couple of examples. In the first one, we have x of t. X is a function of t, and y is a function of t. And in this particular case, I took x as a function of t and decided to solve that for t. And so just a little bit of algebra, we end up with t is equal to x squared minus 4 over 2. Then take this value of t and plug it in for t in the other equation. And then we just simplify. This is just algebra. There's actually no calculus in this whatsoever. It's just a little bit of algebraic substitution and simplification. Now, once you have this, we take a look at this equation, and it then becomes clear that this is the equation of a parabola. Specifically, it is a downturning parabola with a y-intercept of -3. So if we wanted, we could draw a quick sketch of that. It's going to look something like that. Whereas in parametric form, really had no idea what this graph was going to look like, because we have y as a function of t is linear, x as a function of t is a square root function, but when we eliminate the parameter, what we end up with is a simple parabola. In the next example, we have x is a function of the cosine of t, and y is a function of the sine of t. When you have the functions of sine and cosine, you're going to want to try to use the Pythagorean identity. The Pythagorean identity, you will recall, is the sine squared of t plus the cosine squared of t is equal to 1. And so what we want to do is take each one of these functions and solve it for sine of t, cosine of t. So taking x of t is equal to 4 cosine of t, bringing it down here, I'm simply going to solve that for cosine of t. So cosine of t is x over 4. Same thing with y equals 3 sine of t. Bringing that down here, we solve that for sine of t. So sine of t ends up being y over 3. Now we can go to the Pythagorean identity and substitute in sine of t and cosine of t. So the sine of t is y over 3, and we want to square that. Cosine of t is x over 4, and we want to square that. And when we do that, we end up with y squared over 9 plus x squared over 16 is equal to 1. And that is the equation of an ellipse. So it's much easier to see what we're working with once we eliminate the parameters and we put it in terms of just x and y. Okay, in this example, we're kind of combining what we've done in the previous video along with this video. So we want to sketch the curve described by the parametric equations over the interval from 0 to 16, and then eliminate the parameter to describe y as a function of x. So to use the procedures we learned in this section and in the previous video, I'm going to make a table, and I am going to select my values of t. Because x of t is the square root of t, I'm going to use numbers that are perfect squares, just to make my work a little bit easier. So I've selected 0, 4, 9, and 16 as my values of t because they are all perfect squares. And I could have thrown 1 in there too if I'd wanted to. So when t is equal to 0, x of t is equal to 0, and y of t is going to be equal to 1. And so that gives us one ordered pair. When t is equal to 4, x is equal to 2. Square root of 4 is 2. And 1 minus 4 is negative 3. That's a negative 3, in case it's hard to read. When t is equal to 9, we get the square root of 9 is 3. And 1 minus 9 is negative 8. And finally, we get 4, negative 15. Now, plotting those points, we get some type of a curve. It's kind of hard to tell exactly from these points what we actually have. So I plot those points, and to be a little bit more certain as to what I'm actually working with here, this is a good time to eliminate the parameter. So taking x is equal to the square root of t and solving that for t, you get t equals x squared. Then going to our other equation, y equals 1 minus t, and substituting in t equals x squared, we get y is equal to 1 minus x squared. Well, that is a downturning parabola with a y-intercept at 1. And so now it gives me a little bit more insight into what I'm looking at here. So here was my point. That is going to be my vertex. And then I have some of these other points. I didn't put all the points on here because I kind of ran out of room. And so we're looking at just part of a downturning parabola. And of course, don't forget to put your little arrows for the direction arrows for the parametric equations. Now, you may have asked yourself, why don't we just eliminate the parameter to begin with? Well, that's actually not a bad idea. If you eliminate the parameter first, and then you get the equation y equals 1 minus x squared, well, that's probably a little bit easier to graph. However, you should practice doing it this way because this is one of the techniques that you need to be able to do. And it says sketch the curve described by the parametric equations and then eliminate the parameter. So the question is implying to sketch it as parametric equations first and then eliminate the parameter to kind of check to see what you're doing. Next one, same idea. We're sketching the curve. X of t is equal to e to the t minus 3, and y of t is equal to e to the 2t. So this becomes a little bit trickier as far as selecting points and what this curve is going to look like. So I selected 3 values of t, 0, 1, and 2. I evaluated both of these functions for those values of t and got these ordered pairs. Now, that doesn't tell me a whole lot about what I'm looking at here. All right. So I have a point at t equals 0 here. At t equals 1 is right there. T equals 2 is here. What I can tell is that as x goes from -2 to 4, which is just an increase of 6.3, y is increasing very rapidly. So it looks like it might be an exponential function, but it's not. It looks like it might be an exponential function, and I'm looking at my two parametric equations, and they are clearly exponential functions. So all of this is kind of saying, I'm gonna graph this like it's some kind of a an exponential function. Let's eliminate the parameter and see what happens when we eliminate the parameter. So eliminating the parameter here is a little trickier as far as the algebra goes. Starting with x equals e to the t minus 3, I chose to just solve that for e to the t. Not solving it for t, that would require the use of logarithms, and I didn't want to go there. Not to say we couldn't, but I didn't want to go there because I saw something else I could do. So I have e to the t equals x plus 3. And in the other equation, I broke up e to the 2t into e to the t times e to the t. And I think we can all agree that when you are multiplying e to the t times e to the t, you get e to the 2t. When you're multiplying the bases, you add the exponents. T plus t is 2t. So I now know what e to the t is. So going and substituting this in here and here, I get y equals x plus 3 times x plus 3. And so that is x plus 3 squared, which is not an exponential function, but rather it is a quadratic function. Okay, x plus 3 quantity squared. And that is going to be an upturning parabola. So what we're looking at here is part of an upturning parabola, not an exponential function. So that can give you a little bit more insight as to what you're actually doing here. If you wanted to, you could have expanded this out, gotten x squared plus 6x plus 9. If you wanted to find the vertex of the parabola, you could have used your little formula, negative b over 2a is the x value. And so that would have been a negative 6 over 2, which is negative 3. That's the x value. And then plug that back into the function to find the y value, which would have been 0. So negative 3, 0 would have been the vertex, which would have been right about here. So we're at a vertex there, but I didn't include that in the original point. And so we're got a nice little parabola, upturning parabola going through here. And don't forget to put your little direction arrows showing that this is the direction that we are tracing out the curve as t progresses. All right, so this is how we can tie in together the sketching of a parametric function, parametric equations, eliminating the parameter. Now, another thing that we want to be able to do is the parameterizing of a curve. So this is the opposite of what we were just doing. What we were just doing is we have a pair of parametric equations, and we want to eliminate t to come up with a function y as a function of x or x as a function of y. Sometimes we want to do just the opposite. So what we're going to be doing now is we're going to be starting with the function y equals 2x squared minus 3, and we want to parameterize it, which means we want to create a set of parametric equations that will describe this function. Now, hint, there's many, many, many different ways that you can do this. All right, it all depends on how you define t. Now, the simplest way to define t would simply be to let the independent variable, in this case x, just let x be equal to t. And then if you substitute t in for x, you get y is equal to 2t squared minus 3. So you have x equals t, y equals 2t squared minus 3. That is a pair of parametric equations. So writing it in the proper form, x sub t is t, y sub t is 2t squared minus 3. But that's not the only way of doing it. I could have said, well, let's let x squared be equal to t, or t equals x squared, whichever way you want to look at it. And then solve that for x. So we have x is equal to the square root of t. That just becomes that. And then going back to, x squared is equal to t. So I've let t equals x squared. Going back to this equation, I said, okay, I took out the x squared and I put in t. So I have my other equation right here. And the reason that we want to do this is because this is the way that we need to write the actual parametric equation at where x is a function of t. Here it looks more like t is a function of x. So my two equations written in the proper form, I have x sub t is the square root of t, and y sub t is 2t minus 3. So that is what we call parameterizing a curve. We are writing it in terms of parametric equations. Now, we could, of course, eliminate the parameter. In both cases, if we eliminated the parameter here, we eliminated the parameter here, we would just be going backwards, and we would be ending up with the function that we started with, 2x squared minus 3. And I believe we have one more. All right, so I did this one a couple of different ways. And the first and the easiest way to always do it is just let x be equal to t. And so then just substitute that in there. You get y equals the square root of 3t minus 5. Writing it in the proper notation, we end up with x sub t equals t, and y sub t equals the square root of 3t minus 5. But if we want to be a little more creative, I said, all right, well, I'm going to let t be equal to the entire radicand, everything underneath the radical. So t is 3x minus 5. And so that means that y is equal to the square root of t. And so to write this in the proper form, down here, we need to take the first one and solve it in terms of x, or x as a function of t. Here, t is a function of x. Here, x is a function of t. And so that's just a little bit of algebra. And so x sub t is equal to t plus 5 over 3. And y sub t is the square root of t. Now, are these the only ways of doing this? Absolutely not. There's lots of different ways that you could have gone about doing this. You could make up some ways that would be much more convoluted. And have fun with that. See what other ways that you can come up with to represent these parametrically. All right, that is it for this video. Have a good day.